Hi everybody, this is AP Stats 5.2 notes, first day. So we're going to start talking about some of the probability rules and some of the vocabulary that comes along with the probability. The first one is sample space S, and it's just the set of all the possible outcomes. So if I had a red and a blue marble in a bag, my sample space would be R and B for red and blue, and basically it's just like, what is all the items that I have? So a probability model is a description of some chance process that consists of two parts. You have the sample space S and then the probability for each outcome that could happen out of the sample space. So I'd be looking at what's the probability of pulling a red marble, 1 out of 2. What's the probability of pulling a blue marble? 1 out of 2. What's the probability of pulling one marble out that's blue and red? 0, right? So stuff like that, that's probability model stuff. An event is any collection of outcomes from a chance process. So it's any subset from the sample space, and it usually uses a capital letter to name them. And they usually use it when they're talking about the probability of something. So look at the end of example 1. Do you see how they say the capital P stands for probability, and then in parentheses it's A. It's like, what's the probability of event A happening, of this happening? So in our case, it would have been like, what's the probability of getting a red, right? And it would have been like 1/2. Okay, so that's the event. All right, so it says, what's the sample space of flipping a coin one time? Well, okay, that's fairly easy, isn't it? If we're just going to flip a coin one time, it's either H or it's T, right? If I did it 2 times, it could be H and then an H, it could be H and then a T, it could be T and then an H, it could be T and then a T. There'd be 4 possible outcomes, but only once, there's only 2 possible outcomes. So my sample space is just the H and the T. Right, and then the next thing it says the event that they're worried about is getting a tails within the sample space. So they're going to call that, what's the probability of getting tails? Well, probability of getting tails is 1 out of 2. Okay, next one, what's the sample space for rolling 2 dice? Okay, so that gets a little bit more complicated, right? Because each dice has 6 sides, so and there's 2 of them. So we have a little bit more to work with here. So I created a chart of like, okay, here's dice number 1 and dice number 2, right? So this, actually it's die, I know that. Die number 1, die number 2, right? And there's all of our sample space. We could get a 1 and a 1, we could get a 1 and a 2, we could get a 1 and a 3, and so on, okay? All right, so their question is, what is the probability of event B, which is getting a sum of 7 from rolling 2 dice? So they call it probability of B, capital P, and then the event B. So I'd have to look through all of these and look at all the different ways that I could get a 1 and a 7. I get a total sum of 7. I don't think I can do it with a 1. 1 and a 6 would do it, right? So I have this one right here. I could get it with a 2 and a 5. That would be like right here. I could get it with a 3 and a 4. So that would be like right here. I could get it with a 4 and a 3, a 5 and a 2, or a 6 and a 1. So you can kind of see how many different places I could get a sum of 7. So that looks like 6 different places. So when I do the probability, I am looking at 6 out of the entire sample space, which is 6 times 6, which is 36, and that reduces down to a 1 out of 6 probability. Okay, second thing about probability is, for the most part, they don't care whether you really write a probability as in its end form, as a decimal or a fraction. But if you are getting it from a sample space that has a 36 option, your first number should be a fraction out of 36. If your sample space only has 2 options, your first fraction should be out of 2. Okay, they want to see where you're getting that decimal from. All right, so next one, let me erase this part. Okay, so this part says, what is the sample space of just rolling 1 die? So now we're no longer looking at just 2. We just have 1, 2, 3, 4, 5, and 6 would be our sample space. And then it's, what's the probability of event A, which is rolling a 5? Well, rolling a 5 only happens one side out of the whole thing. So we would say that is 1 out of 6 chances. There's only one way to roll a 5. Only one of the sides is a 5. What's the probability of event B, not A? Okay, what's the probability of B not A means the others of them. So that's 5 out of 6. Or we could have written it as 1 minus 1 out of 6. Right? So that would be called the complement. So we would say that that is not A, would be A complement, would be like everything but A. Okay, you would just say A complement, the rest of it. right? And that kind of makes sense. If it's 100% is the highest percent we can have, and the chance of something happening is 20, the chance of it not happening is just 100% minus 20%. Okay, so that's called the complement. All right, other than that, let's go to basic rules of probability. Now these look really, really complicated, but they're kind of simple. Okay, so let's see how we do on these. The probability of any event is a number between 0 and 1. So any probability you get must be between 0 and 1. And I think we did that in one of our notes already. So that's 0 to 100%, right? All possible outcomes together must add up to 1. So the probability of the entire sample space should add up to 1. If all the outcomes in a sample space are equally likely, then the probability that the event A occurs can be found by just using the total number of outcomes that we want over the total number of outcomes in the entire sample space. That seems pretty logical. That's our basic probability. The bottom is how many choices, and then the top is how many of those choices are what I want. Okay, next one says the probability that an event does not occur is 1 minus the probability that it does occur. And here you can see that notation. It's the complement of A, and the probability of the complement of A is 1 minus the probability of A. If two events have no outcomes in common, the probability that one or the other occurs is a sum of their individual probabilities. Okay, now having nothing in common means that they are what? They would have to be something that you can't have together. Okay, so what would be something that you can't have together? The only thing that comes to mind again is, oh, let's do this one. You're wearing shoes or you're not wearing shoes. You can't be kind of wearing shoes, right? So if I'm looking at those two events, or if I'm looking at wearing shoes and wearing shoes and wearing sandals, or sandals and boots, right? You can't have both of those happening at the same time, or it's really unlikely. Right, so those would be called mutually exclusive or disjoint, okay, when they have no outcomes in common. We usually call them mutually exclusive, but there's another vocabulary word, disjoint, that just means apart from each other, right? Okay, and then the way we would write that is the probability of A and B, and please notice that we are using old set notation here. The probability of A and B is 0. So that means having A and B happen together. Having sandals and boots happening at the same time is 0, the probability of that. Okay, now here is a slight problem with that symbol, is in our world, in English, and means we just want to include everybody if they're part of A or part of B. In math language though, A and B means that they have to have both qualities in place in order for you to list them. So that's why they're saying A and B is 0, because I can't have sandals and boots on at the same time. Okay, the other format of this is this symbol right here. That's the union symbol. This is the intersection symbol. This is the union symbol. And the union symbol, we usually use the word or for that. And again, that's kind of counterintuitive from what we have in English. Right? In English, we would just say, I want this or that. Well, here in union, we're basically saying if you're wearing sandals or boots, we want to include you. So it doesn't matter which one you get to check the box off, but as long as you can check one of them, you're included. All right, so the way I usually remember these is super, super dorky, but here you go. So with the symbol, if you put little eyes above the symbol and it's a sad face, it means not everybody can be invited. It means only special people that are fitting into both groups. So it's kind of a limiting sadness, right? Of if you were having a party, only a few people could come. But this one, if you put little eyes above them, it's a happy face, right? Which means, oh, you get to come as long as you have any of these qualities. So that's when we use the word or, okay? All right, so here, let's try an example. Here's a table of one college class of students, and they were asked a second question, I think. I got this from a book. I think the other question that they were using is, did you have pierced ears? Okay, so that's the yes or the no part. And then what color shirt were they wearing? They were either wearing black or not black. By the way, that's a really easy way when you're doing probabilities. If you're not sure what to write for the other one, it's just not the first one, right? Black or not black. Okay, and then I don't have to list all the colors for the second one, or just say other colors, right? Just black and not black. All right, so what we can see here is that there are people that had both things, right? I can see the 19 that had both of them. Okay, so they're going to say event 1 or event A is wearing the black shirt, and event B is having the pierced ears. So suppose we choose a student at random, find the probability that the student has pierced ears. Well, then I would come over to the pierced ears column. I'd go all the way down to the yeses, and I would say that is 103 out of whatever the total is, 178. Okay, and then if I wanted to turn that into a decimal, I could. Wearing a black shirt, so then I'd go to the black category, go all the way over to the end. That is 90 over 178. Okay, this should look a little bit familiar like conditional and marginal probabilities, right? And then C has pierced ears and wears a black shirt. Has pierced ears and wears a black shirt. So if I wanted to take both of those, I could say it's 103 out of 178 plus 90 over 178. But I want you to consider that these are actually people that you would ask to stand up, right? So if I said stand up if you are wearing the black shirt, right? Then 90 people would stand up. The 19 and the 71 would both stand up. So there's 90 people standing up. If I asked stand up if you have pierced ears, I would have these 19 and these 84 stand up, and that's where I'm getting the 103 from. So if I want them to have both, how do I do that? How do I make sure that they have both? It's really just the overlap, isn't it? Right? It's really just the overlap. So which is the part that I highlighted twice? It is the 19 over 178. Okay, and again, the and, go back up to the top, the and is the sad face symbol, meaning they have to be in both parties in order to be invited. They have to be able to say yes to both answers in order to be included. So that's the 19 over 178. All right. The other thing we want to show you is that this is a table method, and that's really nice when there's only 2 categories. But we could also make Venn diagrams out of these too, right? So I could make this one the shirt, and I could make this one the pierced ears, right? So what number would be in the overlap section? That would be the 19. Right? And then what would be in the rest of the black shirt section? It would be the rest of them, the 71 that aren't already standing where the 19 are. What would go into the pierced ears section? Well, that would be everything except for the 19, so that would be the 84, right? And let's see, what else are we missing in here? We don't have a place to put the 4 from the table. So the 4 would be not pierced ears, not black shirt. They would go out here, outside of it, but still within the sample space. Okay, so some of these, it's really up to you, especially when there's only 2 categories, whether you want to do it as a Venn diagram or a two-way table. Often people have a humongous preference. Tables can handle more than 2 categories, Venn diagrams can or can't. No, they really both can only kind of do, oh, I guess I could do 3 circles with a Venn diagram, right? So once I go to 3 categories, I'm going to have a harder time doing a 3-way table, unless you can think in 3D. I can probably still do some Venn diagrams, okay? Next one, number 5, show that the following is a legitimate probability model. Okay, so that's just making sure it follows the rules. So we're going to first look and make sure all of the probabilities are between 0 and 1. They are. Next thing we're going to do is we're going to add them all together and make sure that they add up to 100% or the number 1. They do. So that to me looks like we are good at having a legitimate probability model. Those are usually the 2 things that you're looking at. You're looking to make sure that there is something between 0 and 1, and then you're making sure that the sum is equal to 1. Okay. Next one, 2-way table probability and the general rule. A 2-way table has an explanatory variable usually across the top. So usually whatever variable they give you first is what's going to go on the top. And then whatever is the other variable is going to go along the other side, on the left side of the table. It says a random sample of 500 US adults was selected. Each member of the sample was identified as a high school graduate or not, and as a homeowner or not. The 2-way table displays the data. Suppose we choose a member of the sample at random. Find the probability that the number is a high school graduate. Okay, so if I'm looking for high school graduate, I'm looking at this column. So we're back to doing, looks like 310 out of 500. Okay, next one. Is a high school graduate and owns a home. Is a high school graduate and owns a home. Well, now they have to say yes to both. Now I'm only looking at that one right there. So that is going to turn into 221 out of 500. And then the last one is a high school graduate or owns a home. Or owns a home. So I want to count all of those people, right? So we want all of the people who said they were homeowners, and we want all the people who said they were high school graduates. Okay, so is it going to be 310 out of 500 plus 221 out of 500? Those are the first two categories we had in A and B. Why wouldn't it just be the two of them added together? So again, you think about all these people standing up when I ask them to. Stand up if you're a high school graduate. All of those people in blue would stand up. Stand up if you're a homeowner. Well, 221 of them would have already been standing. So I don't want to double count those people that were already in both categories. So I'm going to subtract, oh, hold on. I'm sorry, I did not 221. I want to do, this group would be 340, right? So I want to make sure that I'm taking out that overlapping group. So I took the total here and the total here all over the grand total, added those two together, and then I want to take out the one that has been counted twice. So that's a 221 out of 500. Okay, and I would go calculate that and figure out what that fraction is. Let's see, do I have that off somewhere else? No, I don't. Okay, now that's one way to count it. The other way to count it, some people just like to just check them off as they do them. And they go, okay, you want everything. So you want this, you want this, you want this. Okay, I'm just going to add those up and put them out over 500 and I'm done. So an alternative answer, and also totally appropriate, is you could just say I'm going to do 221 plus 119 plus 89 over 500, and we should get the exact same answer. So the formula we're going to give you now for the general rule is that first example, where you just take the totals in the margins and then you subtract out the overlap. So that's the general addition rule for two events, and that is only if the two events, let's see, so we're going to do or, which is happy face. So we're going to take all of the marginal probability for A, all of the ones for B, and then we're going to subtract out the overlap part because we've already counted it twice. Right? So let's take a look at a standard deck of playing cards. They seem to assume that everybody knows what playing cards actually look like, so I've listed them across the top. Those are the numbers or symbols that can be on the card. On the left-hand side are the different what are called suits. Two of them are red, and then two of them are black. And sometimes they will mention face cards. The only face cards are the Jack, Queen, and King. Those are the ones that have people actually on the card. An ace does not, so don't count the ace. All right, so suppose we choose a card from a standard deck of cards at random. Find the probability that it is a face card that is also a heart. So a face card that is also a heart. So I could just go through and I could check them off. A face card that is a heart would be these three. Out of how many? Well, I got to count out how much this is. So this is 11, 12, 13 by 4. That is 52 cards. So 3 out of 52. What is the probability that is a black 7? So if I'm looking for a black 7, I'm looking for this one or this one. That would be 2 out of 52. So it's really easy if you can draw your sample space and you just check off the things you want. What's the probability that if I were to pick out one card, it would happen to be a club? Well, that would be all of these, which is 13 out of 52. And yes, that does reduce down to 1/4 because it's one of the 4 suits. Next one, let's keep going. In the table given above, draw the Venn diagram below. So this is that black shirt one that we just did and we already drew it, right? So let's go see if we can get this one to match up. And here's the symbols for each one of the parts again. So remember, the first thing I always do when I draw things is I always try to fill in the overlap first. So that's the 19. Okay, and then this one is going to be event, let's see, what did we call each one of them? So A was the pierced ears, and B was the black shirt. Okay, so I'm filling in the other ones that were pierced ears, but not the 19, that was 71. No. If I want all the pierced ears, that's 84. And then if I want all the black shirts, that's going to be the 19 and the 71. And then remember, we're going to have the little 4 on the outside. All right. So if I wanted to talk about the intersection of both circles, I would say at A intersection B, or A and B, right? That's sad face. They have to be parts of both circles to be counted. If I wanted to do the intersection of A and the complement of B, so I'm looking where A overlaps with not B, so that would be the 84. Why is that 71? Do I have them reversed? I think we have them reversed. All right, that's fine. Goes against our rule about what's the first thing, what's the second thing, but that's okay, I can cope. Okay, so if I wanted to do black shirt and no pierced ears, so that would be A and not C. So, sorry, A and not B. So nothing in B gets counted, so I can count the 71, and that's it. I can't count the 4 because it's not part of the group of A. In the next one, if you wanted no black shirt and pierced ears, so no black shirt and pierced ears, I cannot use anything in the circle of A, including the overlap, because those would be black shirt people. And I would only want to do inside, let's see, no black shirt and pierced ears. Oh, and, so it's happy face, or sad face, so it has to be all of B and the complement of C. So all of B but not A. All of B but not A. So all of B but not A would be the 84. And then if I wanted to get to that 4, I'd have to say not A and not B. So where are the not A's and not B's, all right? And then our last thing about never just write the answer. Always give them context of where you started getting your number from. So always at least say the beginning fraction, so the number over the sample space to start with. Then you can reduce it. Even if you look at it and you go, I know it's 50%, please don't do that. Please still start with the fraction over the grand total in the numbers, all right? All right, in our next section, we're just going to do a little bit matching and see if we can figure out which picture is which using the Venn diagram types of notation, the set notation. So the first one says event A and its complement the complement of A in sample space S. So we want A and not A in a sample space. A and not A. That would be only this one is the only one that has one circle called A. Events A and B that are mutually exclusive or disjoint. That means that the two circles do not overlap. So that would be the first one. The intersection of A and B, sad face, A and B. Which one shows A and B where they overlap? That would be this one. And then happy face, A union B, A or B, would be everybody in the two circles is allowed to be invited. Okay. Next one, what does mutually exclusive look like in a two-way table, right? So in a Venn diagram, we know they look like this. In a two-way table, you'll have nothing overlapping. Remember, that's where your overlap stuff goes. So I would have two Venn diagrams that would just have all the other numbers in it, right? So one of them would have the, let's see, what would be the first one? It would be in AP Stats. So in AP Stats would be 3, and then freshman would be the other one. Freshman would be 8, right? And then not a freshman and not a freshman and not in AP Stats would be the extra 19 out here of the sample space. All right, so basic probability stuff, part 1. Hopefully that feels relatively easy, a little bit more complicated in set notations and the ands and ors, but we'll practice that some more. Thanks.